total internal reflection. Let's think first of all about our learning objectives. Now in this short video we're going to know and use the relationship between refractive index, angle of incidence and angle of refraction. In fact we're going to focus more on this part here and how it applies to one particular issue, and that is total internal reflection. Now in the previous video we looked at this. This is refraction of light by a semicircular block, and we looked at this. We're shining a light in here. Here's the incident ray coming in this direction here, okay, and as it hits the surface here, here's our normal line here, here's a normal, as it hits the line there, some of it is reflected and some of it is refracted along the boundary here. So as the incident ray approaches the critical angle, which is this angle here, it's about 42 degrees, refracted ray travels at right angles to the normal. So there's refracted ray and there is reflected ray. Now let's look what happens as we increase the angle. Now we increase the angle beyond 42, so when this angle here is beyond 42 degrees, it says there, okay, the incident ray now enters a block at right angle, at an angle greater than the critical angle. No light is refracted. Notice there's no light coming through here at all, nothing is being refracted, all light is now being reflected. So here's our reflected ray here. All light is now reflected at the boundary. This is known as total internal reflection. And we looked at a table of values for various things. We know that water, the critical angles 49 degrees, perspex 42 degrees, glass 41 degrees, and diamond, good old sparkly diamond, has got a critical angle of 24 degrees. So a very, very small angle, not quite like that, but you know what I mean, 24 degrees for diamond. Okay, so let's think now about the uses that we can put this total internal reflection to. Okay, first of all, there is a periscope. Now I guess we've all used periscopes of one form or another, and in this one we can use two prisms. Now two prisms, one up here, one up there. Let's look what happens as light passes through. Okay, as light passes through first prism, it hits the glass here, hits this boundary here, an angle greater than the critical angle. And because it's greater than the critical angle, nothing gets refracted, it all gets reflected. So it gets reflected down here, okay, and then down here it hits this boundary here again an angle greater than the critical angle. So again there is no refraction, only reflection. So you can see there how using two of these prisms and knowing the properties of total internal reflection, we can make a periscope. And periscopes are jolly useful. Think about a couple of uses. Well, this one here, this is a wartime picture here, and the periscope here, here's a periscope. The periscope was used to look above the surface of the water in submarines. More peacetime type, here's a guy here probably watching a golf match. So in golfing people often use periscope to see what's going on. So it's a very, very simple use there of total internal reflection. Now another use is very much a safety one, which is a bicycle reflector. Now here's a reflector that will clip on the back of your bike. And how does it work? Well, as light comes in, the light hits this section here at an angle greater than the critical angle there, okay, and so it's reflected. This point here again, it hits greater than the critical angle, reflected again. Let's look at that in much more detail, shall we? So here we've got this bit here represents, take that bit there, okay, that triangle bit there, that represents what we're looking at here, okay. Excuse me. So there's our triangle. Let's look at light rays. Now they come in, they hit this surface here at an angle greater than critical. Everything is reflected. Again, it's this surface greater than critical, and it's reflected out again. So again, this is a very important safety device using the concept of total internal reflection. Here's another one. Prism binoculars. Now a lot of people have got these. I've got a pair just like this actually. Now suppose we could cut our binoculars in half along this line and see what's happening over here, shall we? Okay, so inside your binoculars, down this point, you've got a lens. There's a lens there. You've got some lenses up here as well, one there, and also inside you've got two prisms. The prisms will sit in this sort of area here of our bins, won't they? Sit there. So light comes in, it hits the first boundary there. Then what happens? Well, because the angle again here is greater than the critical angle, it reflects inwards. It's this one here, and again it's going to hit this at an angle greater than the critical angle, so that will be reflected again. And the benefit of this for our binoculars is we can make the binoculars much shorter. Okay, this helps to shorten the length needed of binoculars. Without these, we'd have a much longer object to see through. Okay, so we're using total internal reflection in prisms here to help shorten the length of binoculars as an optical instrument. The fourth one is more recent use, which is optical fibres. Now I'm sure lots of you have seen optical fibres. They have these decorations, don't they? But what they are, they're very thin, flexible rods made of a special glass or transparent plastic. Okay, and light is totally internally reflected all the way along. There's no leakage of light as it comes along the fibre. Only at the end you get light being produced. Okay, reflected all the way along the fibre with very little loss from one end to the other. And here we can see inside what's happening inside. Light enters the optical fibre and hits this boundary here. Okay, here's the boundary there. Now here, because it's greater than the critical angle, you get total internal reflection. Hits it there, again total internal reflection, and this carries on all the way along the optical fibre without any loss at all. Uses, well, we can use this for carrying telephone calls, we can use it for carrying computer data, and also use it for endoscopes, we'll see in a moment. The advantages of optical fibres: they can carry much more information than ordinary cables of the same thickness, and the great thing about them is the signal does not weaken much over long distance. You don't need constant repeater stations to boost the signal. The signal to not weaken as much over long distances, therefore they're much more efficient. Mention the endoscope. Here is an endoscope. Now an endoscope, never had this, don't actually look forward to this if I have to have it any day, is swallowed. It's a tube that's swallowed down the esophagus, okay, goes down the esophagus, and then it comes out in the stomach, for example here, and the surgeon can look inside, in this case look inside the stomach. So it's a long thin bundle of optical fibres that can be used by surgeons looking inside the body. Not a very pleasant process to actually undertake, but can be life-saving, can't it? So it's a great use there of optical fibres. So we've seen here what causes total internal reflection, and we've seen 4 very important uses of that principle. So I hope you've taken on board what we talked about. Please go back and have a look through if you're not sure. But thanks for watching, thanks for listening, and bye for now.